Please don't forget again. And then hopefully on YouTube I can. Before I forget, this is very. So before we start, does everybody have things downloaded? At least the people who are already using Python. Okay, great. So if you run the notebook, you will already get the plots and everything. But today we want to see how we got these plots and so on and so on. So let's wait a few more minutes for everybody to dial in and to appear and so on. So we can get started. Hey, yeah, I think close it. I think people who are late will. Yeah. They're not afraid to come in.
Don't forget to start recording.
I started already. But thank you. Don't stop reminding me because next time I will.
It's the kind of thing I forget.
Yeah. Well, if we all think about it, it won't happen again. So it should be fine. Okay, let's wait a few more minutes. I don't see people from Hawaii log in, but maybe they're there. Let's see. Oh, there's a lot of people. Okay, yeah. It seems like we are more or less all here. Okay, so we can get started. Okay, so welcome to our first hands-on exercise. This will be a short one. So we will discuss some theoretical stuff that happens. I mean, some theoretical, practical stuff that happens. And then we will sit down and we will go through some code. And actually, the way that I'm going to do it is, of course, I have to check if everything works. So I wrote it there, or I wrote it all yesterday. And then I shared it with you because maybe you wanted to take a look and see how the things are done. But what we will do is we will actually go and run piece by piece from the beginning and see what the things do. And people who are already familiar with these kind of topics, they can go ahead. But first, we'll spend 20, 30 minutes discussing the theory behind what is going on. So what we discussed previously is that we said, okay, we want to measure specific monochromatic intensity, and basically what we want to measure is it spatial and temporal and wavelength dependency, right? So we want to see how bright is the sun at different points, in different moments in time, and in different wavelengths, right? And smaller these chunks are, better coverage we have. I just want to go once again, it's not related to what we are going to do, but in principle we are always looking, when we look at a specific piece of the sun, we always see the intensity, outgoing intensity in one specific direction. There is only one mission today which sort of enables us to see things in stereo, and it's called, surprise, surprise, stereo, right? And in principle we can wait for sun to rotate to see some object from different, or to see some phenomena from different angles, but strictly speaking, as the time goes on, and that object is going to change, so we never can really guarantee that we see the same thing from different angles. Okay, so basically today we are going to talk about images, and in principle you can think about it in different way. In the following way, we have tuned our instrument to a specific wavelength, and we made an image, and now we want to see what happens to that image. And in principle, that image is just a set of, intensities or wavefronts coming from different points of the solar surface, coming to our telescope. And then in the last class, we saw that at the telescope, at the entrance to the telescope there is diffraction there, right? And under ideal assumptions that this telescope aperture is circular, we're going to get a PSF that has the shape of area function. Today we're going to go a little bit further and we're going to see what our atmosphere does to that wavefront, and special thanks is to Dr. Jose Marino from NSO, who shared his slides from last week's workshop in California that some of you have attended. Okay, so we have seen this previously, that we have a circular aperture, diffraction through the circular aperture makes the shape of the area disk. Please always be aware of the fact that what comes in here, in all these examples, is a delta function in direction. Okay, so this is radiation coming from one specific direction, right? So each of the points, each of the pixels that you're looking at the solar surface is going to create a different wavefront. And they're all going to separately diffract and create an image here. So strictly speaking, the image that you get is going to be overlap of many area disks, of many delta functions, which all together make the image of the sun. Okay, and in theory, if the hole here is circular, you have this Bessel function over rho. You have basically the area disk, and we have seen that in 3D it looks something like this. However, situation is, and we also went through this. We have seen that when we have light coming from two directions, it's going to create two area disks centered at two different positions, and depending on how close these things are, we will be able to separate them or we won't be able to separate them, and that basically depends on in ideal case, it depends on the size of our telescope. And let's see how that would work when we observe the sun in the very, very ideal case. So what you see here on the right-hand side is an image of a solar surface in continuum, synthesized from magnetoid hydrodynamic simulation. So what people did here is they did basically the simulation of one chunk of the solar atmosphere, and the simulations are done at very high resolutions. So the separation, the pixel size in these simulations is typically from few kilometers to few tens of kilometers. Okay, and then what people did here is they degraded this synthetic image according to what DKIST should see, and DKIST's resolution should be at 500 nanometers, should be something like 0.025 arc seconds, which corresponds to roughly 19 kilometers at the solar surface. And this is actually super cool because this is very close to the resolutions of the simulations. So if DKIST works as intended, it should basically it should reach the levels of the simulations that we have today, which means we will be able to more or less directly compare them, which also in a way means that simulation people will have to work harder to make bigger and more dense, more fine simulations in a way. However, the situation is never going to be so ideal, and the reason why this is so is because in between the sun and our telescope there is the atmosphere of the Earth, right? And actually this atmosphere is, so let's imagine that the light is leaving the surface of the sun. We now know that there is not the surface, but there is the atmosphere, and it's traveling to us. And the last small piece of its travel is this Earth's atmosphere. However, most of the things happen here. We know that our atmosphere is much, much more dense than the interplanetary space. And in principle, you can imagine that things evolve in this way. You have the plane wavefront reaching the top of the Earth's atmosphere, and then comes the Earth's atmosphere, which is very wild and very inhomogeneous. And the main thing that happens there is that the air of different temperatures and different densities has different indices of refraction. And you might remember from your optics classes that different indices of refraction create different, let's say, phase changes, right? If I have two ideal monochromatic plane waves, one traveling through glass, the other one traveling in parallel through the air, when they go out, when this one goes out of the glass, it will have a different phase than the other one. Okay, so strictly speaking, what happens here is we have this atmosphere, which is very inhomogeneous. The plane ideal plane harmonic wave goes through, and then it ends up with its phase being distorted, right? You take this one. And then this distorted phase reaches our telescope. Okay. And the way that you can imagine it, it's something like this. Like in the ideal case, we would have, so this is even without the diffraction of the telescope being taken into account. You have the wavefront here, and it's one nice ideal wavefront being focused in one point. However, if you have the distorted wavefront, it's being focused, it's as the light is changing direction of coming, right? And then it's being focused in different positions here. So we see already now that this atmospheric distortion, or as we call it, atmospheric seeing, is going to spoil our image, right? And one way to imagine that is to say, okay, if there was no atmosphere, we would just have one wavefront everywhere with the same phase. Now, the wavefront is coming, but it has different phase everywhere. And actually, in our hands-on exercise, that is how we are going to model it. Cool. So what happens in practice? How does this change? So we have seen ideally that if you just have a telescope and you calculate this so-called point spread function or the diffraction pattern, it should look something like the blue line here in this plot. It's very well defined, right? Well, now when we include the atmospheric diffraction, it's going to be much more spread out, and it's obviously going to blur much more. And here you see the same plots in 2D. And what you will see later is that it won't even be circularly symmetric anymore. We will see it in the exercise that we are doing. And the parameter that determines the amount of this smearing is a parameter called Fried parameter that basically determines the scale of these perturbations in the wavefront here. So now let's imagine that this black line here that says telescope is actually the primary of our telescope, right, or the entrance of our telescope. And now let's discuss what happens with different scales of the variations in the wavefront. So obviously, if the scale is much bigger than the size of the telescope, nothing will happen, right? Because imagine this now varying, but varying over the scale of kilometers, and the telescope is size of meters. So obviously, when the light that enters the telescope will all be in the same phase, and that's sort of nice. However, if this is on the scales of centimeters or tens of centimeters, then the light that enters my telescope will have different phases, right? And then if so basically, what we can say is that if Fried parameter, which is the scale of the variations of the phase, is smaller than the size of our primary, then what determines our seeing, what determines our resolution, is not the size of the telescope, but the size of this Fried parameter here. And typical Fried parameter is something like 10 centimeters, and that is why Momo, in the last class or class before that, said, well, before we invented adaptive optics, all telescopes behaved as 10 centimeter telescopes, right? Which is not exactly true, because sometimes you just get very nice atmosphere, and this Fried parameters is maybe, I don't know, 20, 30, I don't know what's the biggest.
20, daytime, 20.
20 is the daytime, so nighttime probably something better.
For the sake of image quality, yes. If
For
they're bigger, of course, they correct all the things.
Yeah, of course, we are only talking about the resolution now. Bigger telescopes collect more photos, of course. We talked about light buckets in the last class. Okay, so
So the phases, the problem with here you show the phases as a tilt, but also going back. I mean, if the waves at the two sides of the parts of the aperture are no longer in phase, then you don't get the diffraction. Right, you're no longer getting the proper diffraction between.
Well, you are getting the diffraction, but now your aperture is complex.
Right.
We're gonna do that. Yeah. Okay. So the way that we will model this is that we will. Okay, I have a plot later that illustrate it, so we're gonna see what they are. So now some images of how things should look like. So this is once again the ideal case, and please take a look at the zoom here. And actually, Dickies sees already. We think the sun at this resolution, it looks super beautiful, right? So this is how the things would be ideally if we didn't have the atmosphere, if we somehow put our telescope in the space. However, now here is a simulated image, and this is actually a video. So here we have the performance of the telescope in the so-called seeing limited mode, which means that we now have atmospheric perturbations with Fried parameter of 10 centimeters, and we are sort of imaging the sun at 30 frames per second. So we are making one image every 60 milliseconds, right? No, 30 milliseconds. And this is how so you see now that first of all, the image changes. And this is not because the sun is changing on its own. This is because the atmosphere of the Earth evolves, and then our image changes with time because simply the configuration of the atmosphere is different. So simply the points are focused, or if you want, in a different way. And there you go. Since this variation here changes its orientation, then we have the focusing here being centered at different points. Does it make sense? Okay, now maybe I'm explaining too much. Maybe you already know these things, but for me this is always interesting to talk about. Okay, cool. So then if you compare the zoomed in image, you can see that it's much, much, much worse, right? First of all, the contrast between the granules and the intergranules is much poorer. And these small features here, these bright spots, they completely disappear. So if your science case was, I want to use the DKIS to look at the bright spots, and you had observations of this quality, it wouldn't work. Okay? So that is why we invented something called adaptive optics and image restoration to help us eliminate the effects of the atmosphere. And that is what you're going to hear about next week. Okay. So once again, to illustrate this further, this is now on the left-hand side, we have an image smeared by the PSF of the telescope 10 centimeters big. On the right-hand side, we have the image formed by the telescope 4 meters big, but with atmosphere with Fried parameter 10 centimeters. And you can see that basically the resolution looks very, very similar. So in terms of resolution, if your Fried parameter is 10 centimeters, it's as if you had the telescope 10 centimeters big. Of course, your 4-meter telescope still collects what will be 40 squared, so 1600 times more light. So at least you have gained something. However, we want both things, ultimately. Cool. So now the next question is, how do we model this? And I'm going back to the equations, and then later we are going to see how this works in terms of actually coding the problem. So now just to make it simpler, I went back to the 1D case, but of course when we do the exercise, we'll do this in 2D. So let's imagine, actually I wrote here circular aperture just to remind you how the situation looks like. But let's imagine we just have a slit, and now there is a completely nice, plane wave coming from the left-hand side, and on the right-hand side we have the diffraction pattern. We sort of proved or shown in the last class that the solution here at the screen is going to be the Fourier transformation of the aperture here, right? And what I did in the last class is I ran this integral here from minus a half to a half. Now I'm going to change it, and I'm going to say I'm going to run the integral from minus infinity to infinity. And this function here, a of y prime, is what determines where the aperture is, right? So this function is basically the top hat function that we spoke about in the last class. So this is going to be 1 for the locations where I have the hole, where the light can go through, and it's going to be 0 elsewhere. Is everybody cool with this integral here? Feel free to tell me. Okay, and then I took e to the minus I omega t in front because it's a time dependence that is same for all the waves, and we're basically gonna average over time. You sure that this is okay? If you're uncomfortable with this, you can come and talk to me, and we can go through diffraction problems and do the refraction. I just want also to stress something that we talked about last time. So we said that the electric field at the screen is going to be the Fourier transformation of the electric field at the aperture, or just simply said Fourier transform of the aperture. However, the Fourier transform changes the units, right? So if here I have the electric field in meters, the Fourier transform should give me back the units of 1 over meter. That's how the Fourier transform works. Like it goes from the linear, from the physical space to Wave number space or something like that. However, this is not so. Usually in the Fourier transform here, instead of k theta, you would have k, which corresponds to spatial frequencies, right? However, k here is the wave number of our radiation. It's 2 pi over lambda. So and it's constant for given wave. So what actually this Fourier transformation is doing is we would divide that wave number, kx, with the wave number of the light, and we would get a dimensionless quantity, which is basically angle. And that's why I said that Fourier transformation in diffraction takes you from the physical space of the aperture to the angle space, which is the angular distribution of the diffracted light. And of course, this transformation only works when you are a little bit further away from here. In the near field regime, it would be something called Fresnel diffraction, which I don't know if it appears in our instruments. We can discuss it at some other point. Probably not. Here we go. Yeah, because that one is pretty wild. Okay, so this is how it works in the ideal case. So now let's see what happens when instead of the nice plane wave coming from the left, I have the phase distorted wave. So my atmosphere is coming here and it's doing something. So now the situation is a bit more complicated. So now you see that I have the light coming from the left, where each point on the front has a different phase. And I can plot it, and usually what do these blue lines here mean? Well, the blue lines denote the maxima, right? These are like the crests of your waves. So when the lines have different phase, the crests are going to be at different positions. They're not going to be all lying on the same straight line. And the way to model that is to say, okay, the electric field at my aperture is not anymore constant times e to the minus omega t, but it also has an additional term. Sorry, there should be another I here. I fixed it down there. So it will have an extra term which corresponds to the phase, and phase varies with the position on the aperture. So then when I plug it down there in the Fourier transformation, epsilon O times e to the minus I omega t is going to go in front, and what I'm going to have under the integral is going to be the aperture, the shape, right, times e to the I phi, which is the phase lag, which varies across my aperture here, and times this old term that we have here. So what I can do in a way, and what we are going to do in the exercise, is that we can merge these two terms, so A and e to the I phi, into one term and call it complex aperture, right? And that's exactly what we're going to do. Yes, Mom?
This assumes that the phase along the aperture doesn't change too fast, right, with time, because it's going to take different time for a curve, right? But if you work in radio, this might break, right?
Okay, yeah, you are right, but I wanted to ask a question there. Okay, so before we continue, always what we would always do is we would calculate this electric field here, and then we would square it. Can anybody tell me where this squaring comes from?
Because we measure intensity.
We measure intensity, so intensities come from the square of the electric field, and that also implicitly averages over time, right? And then this I to e to the minus I omega t will disappear because it will cancel with e to the I omega t, right? That's how squaring works. However, so that averages over time scales which are much bigger than what time? Not even coherence. That are much bigger than the period of the wave. Okay, in practice, it should actually be smaller than the coherence time if you want to get diffraction, but we're not talking about that now. So what happens here is that since we are averaging over the very, very small time periods, right? I can in principle write this equation for each of the realizations of my atmosphere. I think that's what you were asking. Because our atmosphere will change over scales of, what was it, tens of milliseconds or something like that? Yeah, or milliseconds. So, but 1 millisecond is much, 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 much larger than the period of the light itself, right? So I can always average very safely over 1 millisecond. But actually for homework, you will have to finish whatever we don't do today, but you will get some extra data where you will be averaging over many realizations of the atmosphere. So Jose was kind enough to share that with us as well. Okay, so basically the problem is still the same. We are still doing a Fourier transformation, except for this Fourier transformation, our aperture is complex. It's not real anymore, and it's complex. Why? It's complex because there is the phase distortion due to the atmosphere, and basically the atmosphere makes our aperture complex. Cool. So what are we going to do now is the following. We are first going to create. So we're going to do everything numerically in Python. We're going to make use of all the built-in routines. I'm going to go relatively slowly and discuss with you all the things and show you how you could do this from zero. So people who are not comfortable with Python, you can just follow, and then later you can do it in your favorite code, whether it's IDL, MATLAB, Java, C#, I don't know. The problem is that in some of your favorite languages, you might not have so nice already existing functions. And in Python, we have super easy ways to do Fourier transformations or something like that. So here I just wrote the correct equation just to be consistent. This is how Fourier transformation would like it look in 2D for the diffraction problem. So first thing that we're going to do is we're going to create an aperture, which is basically just going to be an array which has ones where we have the hole and zeros where we don't have the hole. Then we're going to make a Fourier transformation of that to get an electric field at the screen, which finally means that where our camera is. We're going to square it to get the PSF, and basically PSF is what? So we call PSF point spread function, which means it tells us how a point source spreads. It's basically the intensity distribution of a point source. It's intensity distribution of a delta function in direction, right? And finally, to actually get the image of the sun, because sun is an extended source, it has a finite side, it's not the point, we're going to convolve the original image of the sun with the PSF that we have obtained, and we're going to see what our telescope would see, or actually what we would measure. So for that, you need Python with all these packages that they have sent you online, and you need these two very small files. So one is called phase fits, and it contains information about the phase, and the other one is called synth sun, very creative, which is a synthetic image of the sun at 630 nanometers, which is starting to be my favorite wavelength, it seems. Okay, so I'm going to close this now, and I'm going to go through a Jupyter Python with all of you, and we're going to start making it from scratch. So people who have their computers and who are ready to do this, you can also run ahead and so on and so on. People who are just following, I'm going to go relatively slowly and explain each step, and then we also can come back and play with it. So what you can do is the following. We're not going to use terminal display this time. So I'm just going to go to the folder where, sorry, this is my other class. So I'm going to go to the folder, to the directory where my class And you have already everything done in this Jupyter notebook here, right? So I'm going to open this Jupyter notebook and keep it in the background, and I'm going to cut and paste the chunks into a new Jupyter notebook, so we will see sequentially how the things are happening. So to open a new Jupyter notebook, you can do something like that. Jupyter notebook, surprise, surprise. Then I'm going to put this, hopefully this is going to work. And then I can say new, Python 3, and now you have an empty notebook. So for those of you who never use notebooks, notebooks are basically, I don't know how to describe it, they behave as chains of commands executed in terminal. And actually when you run IPython in so-called interactive mode, you get some things like this, right? So they're good because they show you everything that you have executed before. So you see what code was executed before, and you can do and you can very easily do plotting and things like that in between. I hate them because sometimes they're very hard to debug, but for educational purposes, they are very nice. So then, in addition to this, I'm gonna go and open another one. I'm gonna open the already existing one so that we can let's name this somehow. So my Zoom Windows is interfering with this. So I'll just resize window to the appropriate size. Okay, there we go. So let's name this something very generic like hands-on div. And usually at the beginning you want to include some necessary packages and make some settings so that this looks nice. So I found what works for me. So these are a few lines that sort of will modify your display. So they will make your display a little bit broader. And then you have a few essential packages that will enable us to do things that we want. It's so-called NumPy, then Matplotlib, which allows you to plot stuff. I've worked NumPy 2 times, doesn't matter. And then fits, which allows you to read and write the fits files, which we already used in the last class. So now if I do Shift-Enter, this block will execute and nothing happens because this is just importing sign. Cool. Then in the next chunk, now we're already gonna do something. We're gonna make our, it says here PSF, it's not PSF, it's make the aperture, right? So we're doing everything numerically. We're not gonna use array function and such and so on and so on. What I'm literally gonna do here is I'm gonna have a square array of certain dimension, and it's in that square array, I'm gonna make a circular hole. Okay, actually it's not going to be hole, it's going to be the opposite of hole. Right, where there is a hole, I will have the light passing, elsewhere I won't have any light. So what we need to determine here, does everybody see, are you too far away? How is your spatial eye angular resolution? But Niraj, you're the man from nature, of course you see everything. Ben, do you see? Okay, cool. So we have here what I chose to make an aperture, which is going to be 2048 times 2048 points big, right? Then A here determines the actual physical size. So when we numerically write things down, we have things in pixels if you want, or elements. We need to know how big each of the elements is. So I'm going to have the total square, the total grid where the aperture is living, be 2 meters. 2 meters big, so I'm going to have x and y coordinates made using this. Actually, I can do it like this. It's maybe nicer. I will have these x and y make as 2 linear coordinates basically which in this case are identical, so I could have used only one, but it doesn't matter. And then r is going to be the radius of my telescope. So this is basically d half. So this is for 1 meter telescope, so this is more or less like Swedish Solar Tower, right? Which is also like one of our favorite instruments. And then the thing that we're going to do is we're going to make an aperture. And then there's probably a more smart way to do this. Basically, the only thing that I'm doing here is I'm going through a loop, and then I'm saying, okay, if x squared plus y squared, then square root of that is smaller or equal to r, I will set this to 1. And before that, I use this convenient function np zeros to create n times n array with all zeros there. And then what we can do is we can plot this using command like this. And then a nice thing is that when you do shift enter for this, you will actually get the plot right here in your browser window. And now we see that aperture actually looks exactly the way we wanted. So yellow is where we have the ones, purple is where we have the zeros. Python has these very awkward color maps by default, but yeah, okay, we don't even mind now. We can change them later. I'll show you how to do it. Cool. So we have made the aperture now. Let's now, just to see what the phase does, let's add the phase as well, but then we'll continue working without the phase, just to see what would happen, and then we would come back and redo the phase again. So what I'm going to do now, in the next small chunk of code, is I'm going to open this phase fits file, which if you can, of course, first when I send you the file, you take a look at it first, but now I know that it's just 2048 times 2048 array, which contains something. And so actually we will also plot, we can also plot that one. I didn't do that. So what I'm going to do here is I'm going to add a line which says image show phase origin lower. So if you origin lower plots images as real images, so image starts at bottom left. If you don't do origin lower, it plots them as basically as matrices, so they start at top left. Small difference. And then I'm going to make this what we call complex aperture. I'm going to multiply the aperture by e to the minus I in Python is 1j, times the phase. Okay, so let's now execute this chunk of the code here. Oh yeah, I need, okay, the one plot is overwriting the other one. So I'm going to cut this for now. Let's execute this. So this is our phase. And actually, let's also add, let's change the color. Jana, what do you prefer? Gray?
I like the black and white, but I don't know you guys.
I think it's something like this. And then we can do, yeah. So here we have, I presume that these are the radians, right? In this case, we have a very big span of phases here. It doesn't matter, our exercise will go on anyway. So here you see that the phase over your screen, which we have imagined to be 2 meters times 2 meters, is varying quite a lot. Okay?
Sorry, I missed the scale is.
The scale is, yeah, the scale is wrong. So the scale is in pixels, right? But this is roughly 2 meters, and this is 2 meters.
The
Color bar.
The color bar.
The color bar is in radians.
Right?
Yeah, probably unrealistic. We can.
15 radians.
No.
Okay, then we can do something like this. We will convert this to radians now. Let's say that these are degrees.
Yeah.
Yeah, we will do something like this, and this makes more sense.
Yeah.
I mean, it doesn't matter. It just matters that it's big enough that it modifies our wavefront. Okay. Cool. So now what I'm going to do is I'm going to multiply this by I'm going to multiply aperture by e to the minus I phase, or actually it should be e to the I phase, doesn't matter. And I'm going to plot the real part of the aperture. Okay. So if I plot the real part of the aperture itself, it will show me that things are not in phase everywhere on the aperture. So I'm going to get something like this. Okay? So this shows you that, you know, things are in different phase. The different points of the aperture have, some of them are in the minima, some of them are in the maxima. Yes, Mom?
How do you get the phases? Like,
Somebody simulated them. I don't know. We can ask Jose and I can tell you next week. I mean, you have some sort of random number generator that creates some variations for you on the certain scales. So there is free parameter somewhere in there probably, because if we put it to, but I'm not sure. I found this online, and thanks to Christoph Keller for having his website open too, and I could download the data and the more or less idea for this exercise. Cool. But then what I'm gonna do now is I'm gonna ignore this chunk for the moment. Okay. So I want our phase to be just the. I'm for the moment I'm ignoring the phase. We are just neglecting the atmospheric effects for the moment. So now the FFT part comes. Okay, what we're going to do in this chunk of code here is we're going to use the NumPy function called FFT2. 2 stands for two-dimensional, and what I'm doing now is basically I'm creating a new array called aperture FFT, which is the square of the which is the two-dimensional Fourier transform of my aperture function, and then I'm taking the absolute value and squaring it. I am doing these two things just because I never trust whether this is going to give me a real result, so I just but it's probably not needed, right? So here we now have our BSF, which is basically the electric field at the screen squared. And then there's only one thing which is peculiar to this specific numerical implementation of the Fourier transform. It's that you need to use this function FFT shift to put all the frequencies in their place, because the FFT by default will give you the smallest spatial frequencies at the beginning and at the very end of the array, and we want them in the center. And then finally what I did is, because again this file here will be 2000 times 2000, it will give you very, very wide BSF. We only want the inner parts of that, so I'm only going to cut and focus on the innermost 200 times 200 200 times 200 points, and then I'm going to plot what we get here. And here we got something that I actually didn't want, so I'm going to rerun the code from the beginning. Oh, so we should get something like this. So you will see that you get basically a picture, which is probably ugly from your direction, that has one small point in the middle, and then there is something around which looks a bit like area function, but the further you go, it looks much, much different. And the reason for this is because we are doing a numerical Fourier transform of something that is actually not our, right? I mean, ideal Fourier transform would be infinitely big screen with a small hole in there, right? So there are probably tricks to do this. It's just that I don't know them because I don't generally do this, but this will work because when we introduce the phases, this will smear a lot and we'll get much nicer situation. And this is also in log scale, so basically this pattern here is dominated by the central ones. Cool. So now we have the PSF, and just to convince ourselves that this PSF looks the way it is, we're gonna convert the coordinates in the proper way, and we're going to plot the variations of the PSF at the center to see if they look like the area function, right? So first thing to do that, and this is something that if we really go through this in a lot of detail, it will take us a lot of time, but it's still good just to see what I'm doing here. So first of all, this array here that I call XF is basically the array of spatial frequencies that your Fourier transform will transform to, right? So we said that Fourier transform always goes from the physical space to the space of spatial frequencies. If we are talking about time, it would go from regular time to the frequencies, and so on and so on. And the array of frequencies would look something like this, okay? Because the smallest frequency that we can see is 2 times the 1/2 times the step. Okay. And then I said that these spatial frequencies are basically the product of the wave number of my, which corresponds to my specific wavelength, times the angle. So I want to convert this into angles. To convert this into angles, I need basically to divide it with 2 pi over lambda, which means that I need to multiply it by lambda, and then I'm multiplying by 206,265 because that converts from radians to seconds. This is a magical number that all astronomers should know by heart. I'm kidding. And where did 2 pi disappear? Well, some of you who really pay a lot of attention might have noticed that usually in math books and in these numerics books, Fourier transform has 2 pi in the exponent, right? Here we wrote it without the exponent in our derivation. So these 2 pi's would basically cancel. So that way, from the array of my transform space that I called XF, I can go to the theta, to the angles, and I'm also going to restrict myself only to the innermost 200 thetas. Then I'm going to normalize PSF with respect to the maximum. That's what I'm doing in these 2 lines here. And I'm going to plot one of the, this PSF is still a matrix. I'm just going to plot one of the central rows to see what comes up, and I'm going to limit it to these, to x from -2 seconds to 2 arc seconds, and only for the very small values. So let's see what comes up here. So we get something like this. So we get a very, very narrow PSF and very nice one, which actually will be more prominent if I rerun this all for a smaller telescope. So situation would become more obvious if I rerun this for something like this. So let's see what comes up. So now this looks much more as a Rayleigh pattern, right? I mean, a smaller telescope, so now light is more diffracted. So this looks like a proper airy disk. And here we actually see the secondary maxima of the PSF. And one way to see that you are doing things correctly is that this secondary maxima should be something like 0.017, and it actually is something like 0.017. And this minima here shows you your angular resolution at this wavelength. So this is somewhere 0.75 arc seconds, right? And it sort of makes sense, right? We made the radius of the telescope 10 centimeters, so it's 20 centimeters. So spatial resolution is somewhere under 1 arc second at 630 nanometers, so that all makes sense. Cool, so this, so far, are there any questions? Is the process of what we did, does it make sense? So we took the aperture, we just played a little bit with the phase, we didn't take it into account now. We did the Fourier transform of the aperture, we squared it, we used the original space grid to get the frequency space grid, and then from the frequency space grid, we went to the angular space grid so that we could plot something like this. Okay.
What
Yes.
aperture did you use now? Sorry,
I changed radius to 10 centimeters, to 0.1.
10 centimeters.
Yes.
That's the only number you need to change because everything there is.
Yeah, but then you need to rerun everything.
Yeah.
Yeah.
But it all falls down.
Yeah,
Even
it all-
phases. All the phases.
I ignored phases for the moment. Well, phases are, you see the smaller chunk of phases. So in principle, you could also play with your phases too. But it also makes sense because the smaller telescope you have, the smaller phase variation you see, right? Okay, good. So let's move further. And now comes a relatively tricky numerical part. And that is that the next thing that we should do is we should convolve our image that we don't have yet. And actually, I'm going to first show you the original image of the sun. So let's go back and let's load the image of the sun and plot it. So now you can open this file, sun.bits, and you can plot the image. And I'm going to do something like origin lower, and I'm going to go CMAP is magma. Then you have the image of the solar surface. So this is a 512 times 512 image that I'm sorry, Ben, I didn't get that to use yours, but we can put them, we can give them for the homework. This is quite sun simulation by Matthias Rempel. Originally, it's something like 1500 times 1500 image. That's a lot of pixels. So in order to synthesize the spectra, because this is, the simulations don't provide you with the intensities automatically, you need to calculate them after that. So I just rebinned it to by 3. So this is a 500 times 500 image. And rebinned, the size of one pixel here is 48 kilometers. So if we really wanted to simulate decreased observations, we couldn't. We would have to use the high resolution, but since we are playing here with the much smaller telescope parameters, it's fine. Okay. So now what I'm going to do is, now what we want to do is we want to convolve this image with our PSF. However, the problem is that the grids, this is now a purely numerical thing, is that the grids that we have our PSF and our image are not the same, right? Our image grid depends on the original spatial grid of the aperture that we used, right? This corresponds to the resolution in the MHD. So what I'm going to do is I'm going to interpolate the PSF grid onto this grid. And to do that, I'm going to use the fact that 48 kilometers, that basically 1 arc second on the sun, or 1 arc second of the space, corresponds to 725 kilometers on the sun. So let's use this part now to, so I'm going to do something like this. So I'm going to have this variable here called scale. I know that I know that basically my my grid for my PSF should span about 64 points because I wanted to go from minus few arc seconds to few arc seconds. I'm going to import this SciPy interpolate module, and then I can use these few lines here to interpolate my PSF from the original grid of angles onto this new grid of angles, which has the same spacing as my image, right? So the goal is to have them on the same space. And then I'm going to plot you the new PSF, right? We don't need this peak here, that was just left. And then when we plot it, you see that it looks like your old PSF, except it's a bit more grainy because now we only have 64 times 64 points. So now I can finally do the convolution. And the situation is very simple. So I'm going to explain you what this chunk here does. So I'm going to import from SciPy signal, I'm going to import convolve 2D. Okay, and that just does 2D convolution. Another neat way to do it would actually to use Fourier transform for convolution. So you can now take Fourier transform of the image, Fourier transform of your PSF, multiply them to the Fourier transform back. but there you probably need to take care to dampen some frequencies and so on to get a nice result.
This is a convolution in real space.
This is convolution in real space, yeah. So we already loaded the image, so we don't have to do that. To get reasonable quantities, we want to have the function that convolves, we want it to sum to 1, right? In order to preserve the total power contained in the original image. So what I did here is I just divided my interpolated PSF with the total sum of that array. So in that way the sum, because convolution in numerical way is just going through some arrays and summing their products in a way. So it's actually pretty simple. So I want to be sure that this PSF here is normalized to 1. And then I'm going to actually do the convolution, which is this line here. It's very simple. You just say convolve to D, the thing to convolve, and then the thing to convolve with. And then I'm going to normalize them both with the mean value of the original image. The mean value should be the same because this convolution preserved the situation. And then because I couldn't really find the convolving mode, which I was happy with, convolution is usually going to create you some weird edges at the ends of your arrays. I'm just cutting these edges here. Actually, I don't even have to do 50. I need to take half of the size of the PSF. I could have done 30, but it doesn't matter. And then I'm going to plot them, right? Vmin and Vmax determine the ranges. I want the plots to be in exactly the same ranges so that we can appreciate the change in the contrast that we're seeing. And then again, I'm going to do the origin lower. And we can do CMAP magma. And here I'm going to do the same. So something is origin. Okay, and finally we get these two images here. So on your own computers you can zoom them, but these are now two images of granulation, right? I hope on your computers they look nicer than on this screen, but also this screen is fine. And you can see that the first image is much more crisp and much more clear than the second one. And one interesting quantity that we can do to convince ourselves of that is to calculate something named contrast. And contrast is basically just the standard deviation of the image divided by the mean of the image. Now we know that our means are 1 because we normalize them with respect to mean. So I can just go and print these two. So I'm going to go something like print MPSDD, calculate the standard deviation for you. And I'm going to print one of the original image and then of the smeared image. And then you see that the contrast of the original one is roughly 17%. Of the convolved image is 0.08%. Yes?
How come the X and Y axes are different? So that goes to like almost 500 and that goes to 400.
That's very interesting. Let's see what we did. See what I did.
Because you cut.
Oh, because when you
You cut
convolve
the
it, it
50.
smears it out.
No, but
But the number of pixels is
the number of pixels should be the same. Let's see what happens. Okay, very good catch. So image shape, image smeared shape. Oh, okay, the convolution then, the convolution probably extends it a little bit. So what I want to do here is, give me a second. I want to cut, let me see, something like this should work. So if I don't cut the original one at all, but I just cut the second one by half of the PSF, so we had 64, right? There are now the edges here, a little bit. But but it's not so bad.
That's what it should be.
No, but I mean they should be, but I don't want them. So let's cut.
You can use mode equals same as an argument in the convolution.
Mode.
Mode equals same equals same in apostrophes.
Like
Yeah.
this,
Yeah.
and then I don't have to cut anything.
Yeah. Because I think the extra stuff comes from the fact when the PSF goes beyond the.
Yeah.
Yeah. It comes definitely from that. But see, it gives me the same that I got before. It gives me this black line here.
But why
So-
aren't you, I mean, that's good that there is a black line there, it should be there, no?
No, because in theory the image is super big. Image is infinite, so there shouldn't be the
Not
black
your
line.
image has got a dimension, you're not. I mean, you're working with an array that has a finite dimension.
No, I agree. But like for example, when I'm calculating the contrast,
Yeah, you should
then
exclude.
I should exclude the
edges from
things.
the
Yeah.
contrast.
So another thing that we can do is there should be something like edges,
Yeah, truncate.
either truncate or wrap, something like that. So there is mode is what? Same, and then boundary we can say sim. And see if that helps the situation. The other one.
Wait, but you're cutting different areas.
No, but that's what I did now. We don't want to cut anything at the moment. I'm trying not to cut anything at the moment. Boundary equals sim. So how about this? Okay, so now it looks a bit better. Before when I used it, it looked a bit weird. But okay, this will, if you use boundaries equals sim and you use mode equals, what was it, full? No, mode
Same.
equals same,
Same.
then it will give you reasonable results. And then when you look at the contrast here, it will be 17% and 8%. So now let's redo this all over again. Of course, we don't have to go through everything, we just change one number. I just want to do this for a bigger telescope to see how the things change. So let's make our telescope 2 times bigger. So let's say, or a little bit more. Let's make the telescope half meter bigger. Half meter is VTT, right?
No.
VTT is 70
It is
centimeters.
75 centimeters.
Let's do 75. Okay. We don't care about the phase still. Let's see how it's calculating. We have a bigger telescope. We have a more narrow PSF, right? You see this numerical noise more pronounced, but it's okay. You also see the PSF plotted in 1D more narrow. Of course, the original image of the sun won't change. Interpolated PSF will now change, becomes more narrow. And then we do this last chunk. And now image is a bit more clear. We have bigger telescope, the image is more clear. We calculate the contrast, and the contrast increased now. So still our telescope cannot recover the original contrast, but the situation is better, right? Now let's go back and put the phase back in. So let's keep this 75 centimeters telescope, let's keep VTT, but now we include the phase. So the only thing that I have to change now, but now pay attention because a lot of cool things are gonna happen. The only thing that I need to do is I need to uncomment this chunk here, right? And we'll plot it. Okay, so, and now I can just start executing from this. So now we are plotting the, oh, I actually hate this, why are you sure? This is the aperture, this is the phase, and now this doesn't work for some reason, which isn't the first time that this has happened. We should see now aperture here with the phase information, but we are not. And this is exactly why I hate the notebook. Okay, so let's save. Let's reload the page. Let's start from the beginning. Hop, hop, hop.
Ilan, I think the phase is in radians. It only goes from 16 to minus 22. I think the phase is in radians.
The original one, you mean?
Yes.
But don't you think
Convert
that
it- when you convert it from by dividing by that, I think it's actually giving you very little variation.
Okay, okay, that might be the case. Let's see if that helps the situation.
Yeah.
Oh, it does.
Yeah.
It looks like it does. Okay, amazing. Okay, so in original, yeah, I thought that this is too big, but it's not too big. Cool. So now we see our aperture. It looks like this. Actually, this is not the aperture. Still looks like a circle, but things in the aperture are not in phase. Now calculate the PSF, and you see that now your PSF is much bigger and is super weird. It's not regular anymore. So people in Boulder really need to look, and I guess the other people with projectors need to look very perpendicular to this. Look at your screens. So you see now that PSF isn't even, it doesn't even have the symmetry, right? Because the things are encountering your telescope and they're all in different phases everywhere on your aperture, and simply the situation is that your PSF is not symmetric. And you can now plot this 1T PSF, and it's gonna look super wild. So it's completely irregular, right? We don't really see, okay, this is obviously the second maxima, this is obviously minima, and so on and so on. We see something different. So now we can jump through this image plotting, we can jump through the interpolation, it looks like this. We can do the convolution and plot these images. And you see now that we now have, again, very blurry situation. And if I plot the contrasts, now my contrast is even worse than with 20 centimeter telescope. It's 0.07, right? So it is not the
20 centimeter telescope with the phase is weird.
yeah, that was the 20 centimeter telescope without implementing the phase. This is now 75 centimeter telescope with the atmospheric perturbation. So now finally let's change situation once again and see what would happen if we had 20 centimeter telescope again. So I'm gonna go back to 0.1 here. Gonna run everything. We're gonna see what comes up. So now you can see that contrast is very, very similar to the contrast that we have obtained with so now this is 20 centimeter telescope with atmospheric perturbations, and the contrast is actually very similar to what bigger telescope gave us. So this is sort of proof that having a big telescope doesn't make any sense if you cannot beat the atmospheric effects. So now what happens in the real life? So this now would correspond to an image that you have obtained on the time scale where these phases are more or less constant. As we spoke before, this time scale is roughly few milliseconds, right? Today we can make such observations. We are there on the limit. So if we really have a fast camera, we can do hundreds of hertz, which means that our exposure is, you know, for several milliseconds, something like that. However, if you let your camera record for longer, if you let your camera record for 1 second, it's gonna record basically a stack of the images that look like this blurred image, just each of them will be blurred in different way. So you will see many different random realizations of your phase. that we started with. And that's actually what you're going to have in your homework. I'm going to give you the time-dependent phase, and you will have to synthesize. You will basically, you can even synthesize the video like the one that you saw at the beginning, but you will basically have to calculate these image properties like contrast and so on for this even more realistic situation, right? And now, of course, keep in mind that here we use this phase information relatively randomly. I just took some file from Christoph Keller's exercises, and I said, okay, I'm gonna interpolate this to 2084 to 2084. 2 meters times 2 meters. I don't know if this corresponds to real phase variations of 2 meters times 2 meters matrix. So maybe Kevin will say something about it next week, like about the typical scales of variation and how much the phase is varying and so on and so on. Okay, we can look at that. But anyway, Joseo promised me that he will give me a code which actually simulates that in a relatively realistic way, so I will share that code with you so you can take a look there. And for the homework, you will have more realistic phase information than this one. So you can now play with this and put any numbers that you want. Be aware though that in principle your hole here at the beginning should be at most 1/2 of the full space. So if we wanted to make the decayist, if we wanted to set radius to 2 meters, we need A equals to at least 4 meters, right? Actually more. If we want R equals 2 meters, we should make A 8 meters or something like that. So let's see how that works. And then we can also disable the phase here because we don't have, it's not so realistic anymore. So let's just see how much decayist in ideal conditions would change the situation. So you see how now the narrow the PSF is. The PSF is super, super small. And actually we don't even see the secondary maxima because they're simply too small. And now you see that there is still some small change in the contrast. However, now my original resolution of the simulation is not even appropriate, right? So here to really see the changes in contrast, we should use the original simulation with its original resolution, which is 16 kilometers, which is almost the resolution of the decayist. Okay. Okay, but I mean, you can use this to now make various kind of interesting investigations, and this was just an exercise to show you basically how to code these kind of things, like to show you that these things are not something scary and undoable. You always see these examples, but now we basically made them over 1 hour or even less. And the other thing is that very often, in order to compare your theoretical calculations or simulations with what we see in the sun, you need to know these properties of your telescope and how to degrade images to compare them. Like very often, you will see many papers, you will see a certain amount of papers which, for example, investigate some technique, and the way that they investigate this diagnostic technique is that they take a simulation, they synthesize the image of the sun, they degrade it according to the observational conditions, and then they apply their diagnostic to that data, because then they can compare what they get from the diagnostics with what originally was in the simulation. And actually I did something like that recently for something we call inversions, and we will talk about it in the second part. So these are all good things to know, right? Very often, and also very often you don't have to calculate your PSF in such detail. Sometimes you have to, because sometimes you're, like for example, if you're working with the space-based data, for example, the data, there is no atmosphere there, there is no phase differences. But your aperture is, as we talked before, is not a perfect circle. It's not tool either. It's not a perfect circle. It has this called spider pattern, because it doesn't have the clear primary, as we would say. So you have to really accurately calculate the PSF. It's going to look very complicated. It's going to be very complicated. I actually also wanted us to maybe talk a little bit about the deconvolution, but our class is now done. So I will try to mention deconvolution at some point. Maybe, Kevin, maybe you will also talk about it. Yeah. So in principle, for some situations, like for example in space, we can, when we don't have the atmosphere, we can try to undo this convolution and to do something called deconvolution and to restore our original image. Those of you who have time and who have free will, who have enthusiasm, this was bad translation from Serbian. Those of you who are enthusiastic about this, you can try to look through Python packages and try and deconvolve the data. So after you have the PSF that you know and you have the original image and the convolved image, try to retrieve back the original image from the convolved image. It's basically just a very big linear system that is still solvable, and I'm sure that Python has routines for that. Okay, questions, comments, critics, concerns? Yes, Gary?
So these phase errors are, maybe they're 15 radians or something, but that's about, there are 1 or 2 waves of air over the surface.
Yeah.
Which is, induced by the atmosphere and the refraction changes. But that's after traversing 10,000 meters of the atmosphere.
Yeah.
And it's, so it's a part per 10 to the whatever, 13th. It's amazing that the phase errors are so small in relation to the path length through the atmosphere.
Yeah. But I mean, to begin with, the index of refraction of the air is not so big. It's like what? This is 1.0027 or 0.00027. So then you have variations of that, right?
Right.
So, but you're right. It's still a huge length. It's like 10 to the 7, 10 to the 8, no, 10 to the 7 meters.
It's 10,000, yeah, 10. About 10
Is it 10,000 kilometers? It's not 10,000. 10,000 meters. Yeah, 10,000 meters. Yeah, but it's many wavelengths. Yeah. True. Yeah, but I mean, you don't even need to have it. It's just if it's order of 1 radian, it's already enough to induce differences, right? Yeah, but then maybe you will tell them next week about like where exactly this happens, in which layer of the atmosphere, and why are the telescopes on the island. So, I mean, we can also talk about this throughout the course. More questions? Okay, this stays online. Something like this will be in your homework. So make sure to go through this. People who didn't sit and work on their computers, make sure to go through this. We can go through another. We can go together through this using another programming language or something like that. I would be happy to help. Okay, thank you so much. I hope that this was useful. And please, there are certainly much better and faster ways to do this. If you have any suggestions, just send me corrected code, and you might even get some extra points. Thank you so much. See you Tuesday, and Tuesday and Thursday we'll be having Kevin Reardon as the lecturer, and it will also be a combination of lectures and interactive work. So yeah, be there. Bye.